Thank you very much. So I would like to thank the organizer for this invitation. I've been really enjoying the talks this morning, and I'm really sorry actually I cannot stay throughout the entire workshop. So today I decided to change a little bit, reshape a bit my topic based on what I heard and based on the time I realize I have, which is less than what I thought in the beginning. Essentially I will present work done mainly by my former PhD student, Juan Carlo Estrada Saldaña, and former postdoc Eduardo Lee. And so this work benefited from important collaborations with material growers from Pisa, the team of Lucia Sorba, and from Eindhoven, the team of Eric Bakkers. And so we also profited very much from the help of some theorists, Ramon Aguado from Madrid and Roch Zicco, and Jean-Michel Niquet from my department in Grenoble. This morning we have already had a little review about experimental work on Majorana fermions in semiconductor nanowires. So this work was very much stimulated by a couple of proposals that came out in 2010, where essentially it was proposed that if you take a semiconductor nanowire with certain requirements and you couple it to a superconductor, you expect to have the emergence of these zero energy modes that fulfill the properties of Majorana fermions. So this proposal is actually, the model is quite simple. The reality is much more complex, and that's also what experimentally has been dealing with since this proposal. So in essence, the key ingredients are, first of all, the one-dimensionality of this material, the semiconductor part. Then we need the semiconductor to be helical, in the sense to have a lock-in between momentum and spin. And this can be achieved by a combination of spin-orbit coupling and a properly oriented magnetic field. Then you need superconducting proximity effect, inducing pairing correlations. And that's about it. But perhaps you can expect that in these materials, other kind of correlation exists. And you may wonder what is, for example, the effect of charge interactions. So this is one of the enemies that we have to deal with. So that sort of sets the outline of my presentation, where in essence I will be touching these two aspects, the one-dimensionality and the role of Coulomb interaction in these materials. So I will speak in the first part about let's say the role of interaction in the 0D limit. And that is essentially because, okay, if you're an experimentalist and you want to deal with interaction, okay, you can say, okay, well, I know my enemy, so I decide to understand it in its most favorable playground. So instead of taking a 1D system where I don't know if it's 1D, whether interactions are important or not, I consider a much more well-defined system, zero-dimensional, where I know how to treat the effect of Coulomb interactions. And the other part is to, okay, let's take the other aspect and look at one-dimensionality. So we will discuss experiments that was done in a regime that is as close as possible to a one-dimensional regime, which is the case of a very, or a relatively short junction, nanowire junction. Okay, so as I said, let's start with the first part. So the idea we have in mind is to replace the nanowire with a much smaller object. So it's a quantum dot coupled to a superconductor. And this is a problem that has been addressed by many theoretical works. And you have an analog in bulk, which is the case of magnetic impurities in a superconductor material, for example, manganese in lead. So this problem can be modeled with a relatively simple, at least formally, model, the Anderson model, that is consisting of basically a quantum dot with just one spin degenerate level that can be occupied by no electron, one electron, or two electrons. And in this problem, you have essentially the following characteristic energy scales. So there's the gap of the superconductor, the charge energy, the energy cost that you pay to add or remove an electron to the quantum dot. This gate-tunable quantity basically is the energy position of the electrochemical potential of the quantum dot that can be tuned with the gate voltage. And this is the tunnel hybridization between states in the quantum dot and states in the superconductor. So let's try to guess what would look like the phase diagram of this system. So it's to understand that, it's convenient to look at some limiting cases. For example, first of all, we should understand that in this material there are two fighting effects. So superconductivity likes to pair electrons, so would like to add electrons on the dot in pairs. So you would like the dot to be either empty or fully occupied by singlet states. And you have Coulomb interactions that, on the other hand, would like to pay the least possible cost. So the least possible cost is the one associated with changing the number of electrons by just one. Okay, so if we sit, for example, in the, let's say we write down this phase diagram in terms of this adimensional parameter. So we put on the x-axis the energy level of the quantum dot scaled to the charging energy. And so in this particular case, so if this value is above 0, it means that your level is above the Fermi energy of the lead, and then so it's empty. So here we have empty state. Here we have, in principle, we tend to occupy the state with one electron, and here we lower the level such that a second electron can come in. So here the occupation will be around 2. And so in the limit where here on the y-axis we have the coupling to the superconductor, in the limit where the coupling is very small, gamma s over u close to 0, so then we can expect Coulomb interaction to dominate over the superconducting proximity effect. So we can expect that then the state will be, let's say, a fully empty state, so therefore a singlet state over here. Then by lowering the epsilon naught, we will add one electron to the quantum dot, so the ground state will be a spin doublet, so that where the spin can be pointing either up or down. And then as we keep lowering the epsilon naught, then we can add a second electron there and then go to a singlet state with two electrons with opposite spin occupying the single energy level. In the very opposite case, imagine that you are up here, so that basically charge interactions are not important. So when you are here, the dot will be empty, of course. And then when we start to be the level to start to be accessible to electrons, then immediately two electrons will be able to go in. And therefore, there will be a singlet type of state. There will be a combination, a linear combination of a fully occupied and a fully empty state. So it's a singlet state of Bogoliubov type combination of these states. And now it's interesting to understand that, for example, if you sit around here, so in the middle of this, in principle, n equal 1 regime, that means that you will have an equal combination of these two components. So V or U in modulus will be equal to each other. But on average, you will have an even number. So you will always have an even number of electrons on the quantum dot. Good. So, and of course, OK, what I didn't say is that if you interpolate these two regimes in the simplest possible way, then you get this kind of lobe structure. So you can almost draw it without knowing anything and just by this analyzing these limiting cases. Now, in this problem, then the lowest energy excitation will be very simple. So if you are in the singlet state here, then the lowest energy excitation will be the transition to the doublet excited state. And this transition involves a parity change. You go from an even parity to an odd parity. If you are in the doublet, the reverse transition will be the lowest energy transition. So this excitation can take different names depending on where you look. So if you think about magnetic impurities, They are often referred to as Shiba state or U-Shiba-Rosenov states. And if you think about mesoscopic physics, typically they are known as Andreev levels, so this is excitation. And you can investigate such transition, for example, by tunneling spectroscopy. And what I will show is experiments done in this kind of setup, where you basically connect a normal metal contact used as a tunnel probe to your coupled quantum dot superconducting system. And this is work also. This is an idea that was pursued already in earlier work. And the analogs of the experiment are experiments done in STM, where essentially here we have a fixed tunnel probe where the tunnel coupling is modulated by a gate, is controlled by a gate voltage. In an STM, the analog is to just adjust the height of the tip on top of the impurity.
But the experiments are two superconductors in a sense. No? You have one normal method. One
even in STM experiments. Well,
I thought that in order to see this nice bound state, everything they need to do with the superconducting tip.
No, also with normal tips.
No.
Well, I did with both, but also with in the same artificial.
Yeah, just a question also.
Okay, so here is an image of the device that we use. So we have a nanowire laying on a bed of gates, and it is contact on one side with a normal contact based on titanium gold, and on the right side with a superconducting contact based on aluminum. And so you have, in particular, you have one bottom gate over here that you use to control this epsilon naught. And as I will show you, we can use also a back gate here that is doped that we will use to tune mainly the tunnel coupling between the quantum dot and the superconductor. And for some reasons, during fabrication, essentially we end up having a strong coupling to the superconductor and a weak coupling to the normal metal. So the contact is much better to the aluminum than to the titanium gold. So that's why I kind of draw schematically this quantum dot that is shifted towards the superconductor to stress the fact that the system, this is just a weakly coupled probe, and the system I'm considering is mainly quantum dot coupled to superconductor. So that's the regime, the experimental regime. Okay, so what we need to do first is to find a regime where our system behaves as another zero impurity. So it's easy to look for it in a normal regime. And since our superconductor is aluminum, we can suppress superconductivity with just 30 millitesla. And then look for signature of undersea impurity. And these are well known in quantum dot physics. These are Kondo effect. So you search for a regime where you see a zero bias resonance in a Coulomb diamond. So this will be a regime where the number of charges on the quantum dot is equivalent to 1, even if it's more, but it's an odd number, let's say. And this is an empty case, and this is a fully occupied singlet case. So now, if you turn off your magnetic field, so this stability diagram changes, and you find some low energy excitation. Note that the energy scale here are 200 microvolts, so it would be a very narrow window in this plot over here. And I didn't check my time. And so these lines that you see over here, these are resonances associated with the elementary sub excitation. So these are the Andreev level of our systems. And so now it's interesting to interpret these lines. So if you sit over here, you are in a singlet ground state. So these lines correspond to the excitation from singlet to doublet, whereas in the middle region, they correspond to excitation from doublet to singlet. Now it's interesting to see what you would expect if you increase the tunnel coupling. So this would correspond to moving this line that you cut across the phase diagram up in the phase diagram. So in that respect, you will expect this lobe to reduce in size and eventually disappear. So let me show this in real life. So you start with this measurement, and then by changing the backgate voltage, empirically we find that we can actually modulate the tunnel coupling, so we can move up in the phase diagram. And if we do that, then the loops decreases until here we are basically tangent to the phase boundary. And eventually, the two excitation move apart, and you have a line cut through a fully singlet region. So this qualitatively is exactly what we would expect. Now, can we be more quantitative? So to do that, we need to know the parameter, the physical parameter of our problem. So we need to know, in particular, we need to know the tunnel coupling and the charge energy of our system, which eventually, these are those that determine the Kondo temperature of the problem. So we see here that as we vary the backgate voltage, the Kondo temperature is increasing, for example. You see the Kondo resonance gets wider and wider. So we can actually measure its dependence on these parameters. But so what we decided to do is to actually fit the normal regime, measure at around 30 millikelvin, 30 millitesla, sorry. So to fit it with an energy model. And so you see that's the best way, let's say, to extract the two parameters. There's actually no way around to extract the true physical parameters. So we fit our normal state curves, and these eventually give us a set of table with all the parameters. You see here the charging energy is a function of this backgate voltage that is tuning the tunnel coupling. And so you see here, as a function of backgate voltage, how the tunnel coupling is increasing. So once we have these parameters, then we can inject them again into the energy model, add the superconducting proximity effect in the Hamiltonian, and then compare our measurements in the superconducting regime to the measurements, to the calculation, the energy calculation. And you see that the agreement, even quantitatively, is quite satisfactory. So we can also, basically from here, from these points are the phase transition from doublet to singlet. So they can be used to extract the phase boundary, the experimentally measured phase boundary. These are these dots over here, and the lines are the theoretically calculated phase boundary with the same physical parameters. So again, the agreement is pretty good. And now here is something that I would like to point out that we will see again in a moment. So if we sit now in this doublet regime, we expect that if we had two superconducting contacts, then the corresponding Josephson relation will exhibit a pi phase shift due to the spinful ground state. Whereas if you are in the singlet, there will be a conventional Josephson relation. So we also measure let's say the energy level of the Andreev states as a function of this dimensionless parameter is the Kondo temperature over the superconducting gap. So you see that if the Kondo temperature gets very large, it means that our coupling becomes very strong. So we favor a singlet ground state. Whereas if our coupling gets very small, so this parameter decreases, we favor a doublet ground state. And there is this phase transition that occurs at this ratio of the TK over delta, which is in good agreement with old predictions from Satori et al. Now, in an earlier experiment, we also investigated the effect of the magnetic field. So if you apply magnetic field, you will see that if you sit in the singlet state, then over here, sorry, then you can resolve these two transitions. And so the Andreev state splits due to the Zeeman effect. And as it was also shown this morning, so this splitting of the Andreev levels then can result in the emergence of some zero bias anomaly, as shown over here, because two of the Andreev states basically go together and meet at zero energy. So this zero bias anomaly, in some sense, can be seen as a sort of precursors of Majorana fermions. I think it was very instructive to look at this theoretical paper from the Dasarma group at that time that showed that, in fact, you can go in a kind of continuous way from trivial Andreev states to Majorana fermions as you make your quantum dot longer and longer. So basically, the Andreev levels tend to localize at the edges of the quantum dot, and correspondingly, you tend to go towards a regime where they tend to stick to each other around zero energy. So in that respect, I think is why I'm saying this, because I think it's quite useful to look at even in a limit that is not probably ideal for Majorana fermion, but going from quantum dot and then trying to understand how to make, let's say, how trivial Andreev levels evolve to non-trivial ones. It's a quite conceptually interesting idea. And it was to some extent explored in the Copenhagen group. So, so that concludes my first part on the role of Coulomb interaction. But that's not over, actually. But now I want to discuss more the quasi-ballistic regime. So ballistic transport in nanowires has been observed to some extent. We have seen also this morning. So I think, first of all, it's easy to observe it at very high magnetic fields. The first experiments was from the Delft group that shows some conductance quantization at rather high magnetic field. And that is because magnetic field tends to suppress the backscattering of electrons. So these are our data. For example, I originally planned to discuss about this, but no time for that. But just to show them, there are some nice plateaus at 5 Tesla that in the same material, indium antimonide. And these are the structure that were measured in that were discussed this morning, where conductance quantization was observed also at zero magnetic field. But I want to stress the fact that in all this structure, actually the length of the channel is rather short. So here we're talking about a few hundred nanometers, and here as well the channel is rather short. So it's kind of convenient to look, if you search for one-dimensional effects, you want to be in the most favorable situation, so have channels that are as short as possible. So these are some other data, not published, obtained with the indium arsenide nanowire. Again, the channel is around 200 nanometers, and you see quantization at multiples of V square over H at high magnetic fields once again. So now I'm going to show you now in this an experiment where we look at a quasi-ballistic regime. So again, the channel is quite short, but we add another ingredient, which is the possibility to have multiple gates with which we can tweak the potential in the channel and make it as ideal as possible. That's more or less the underlying idea behind this experiment. You can cure possible inhomogeneities or possible bumps in the potential and have a system that is as ballistic, looking at ballistic as possible. So there's this additional degree of freedom. Another ingredient that we have is we use Tantalum superconductors that was mentioned by Sébastien. And tantalum is a material that exhibits a superconducting transition. Actually, there are two phases. One of them has a superconducting transition around a bit below a Kelvin, and the gap is around 80 microvolt, and this is the one that we end up having. You can have a phase with a 4 Kelvin transition, and what is interesting is that the critical field is very large. It is 1.8 Tesla, and that is because tantalum is a very heavy metal with strong spin-orbit coupling, so it's quite hard to kill the superconductivity despite the small energy gap.
Excuse me?
Yes?
The G factor was large. How large in figures?
Well, in this material, it was not super large. This is indium arsenide. It's around 11, something like that. Still is large enough to split the states and as compared to, killing the superconductivity in the leads. So we can induce an important Zeeman effect. That's the key of the experiment I'm going to tell you. So, okay, so as I said, we look for superconducting ballistic regime. So the ideal to look in the high magnetic field regime. And so this is a plot of the conductance. And now you can imagine that these two gates that we are varying, the gate 2 and gate 3, kind of modulate the barrier, a kind of camel-shaped barrier. And so we can adjust them to have the conductance as ballistic as possible, and the ballisticity will emerge as plateaus in the conductance. So in fact, If you look in this regime, the conductance is around 0.9 E square over H. And in this regime is around 1.8 E square over H on average. But there are some fluctuations of around 10–20%, which indicate that the system is not exactly free of some backscattering effects. In fact, there are resonances you see that evolve mainly in this direction that could be associated with some localized state. But what we can do, what I want to show you is that you can, for example, vary this gate voltage G2 and choose one voltage, for example, this blue line, where there is a nice plateau here at conductance. Well, it's not exactly 1 E square over H. There's some finite transmission at the level of the contacts, but it's 0.9, very close. But it's a pretty flat plateau. However, you can see here this pretty flat plateau has been cured. And I've chosen this gate voltage, but if I move with the gate voltage, here it will become with a little bump, and here it will become a little suppressed. So if I had only measured this, if I didn't have this possibility to tune both gate voltage, I may say I have a nice conductance plateau. Instead, we know from this tunability that there's something else underneath. There are some states that are localized and that play a role. So, but anyway, let's pick up this as ideal as possible regime and then look at the evolution in magnetic field. So if I reduce the magnetic field, this plateau shrinks, as one would expect, by reducing the Zeeman split in the wire. I cannot go below 1.4 Tesla because, so I can go, but when I go below 1.4 Tesla, the superconductor, the contact becomes superconducting, and then the conductance overshoots. So I cannot follow anymore my plateau. So here is the same plot in a color scale, where you can see that the plateau shrinks, but the extrapolation goes to a finite separation of this line. So we can interpret this as the presence of some residual charging energy, and so this separation is not simply the Zeeman energy, but it's the Zeeman energy plus local charging energy. And that's what we can estimate by looking at the nonlinear regime, so I can skip on this. So now, if I wanted to access the normal regime here, so the normal conductance here, I have two ways to suppress superconductivity. Well, one way is obvious. One is to raise temperature. So if I raise temperature, what I find is, again, a plateau that is approaching 1.8, but there is a shoulder over here. And the same shoulder I can find if I measure the conductance at finite voltage, well above the gap of the superconductor at low temperature. So this shoulder we interpret as a reminiscence 0.7 anomaly effect. It's well known in quantum point contacts. And for example, in this experiment from Cronemet and co-workers, Charlie Marcus and so on, this effect was associated to a Kondo effect, so due to some localized state in a QPC. So it happens even in the clean, almost the cleanest QPCs. That's a bit the message. And we have it here. And so what we think that we have a localized state. And so we decided to investigate this again by modeling with some energy. And also we assume that there is a localized state, and there is a quadratically increasing gamma with the gate voltage, because what we need is we need a plateau, and then we need to evolve to some kind of non-interactive regime with a constant conductor, or almost constant conductance. And that can be achieved if you assume that your gamma, your coupling to the superconductor, increases with the gate voltage. So with these ingredients, so the problem has the following energy scale. So there is a Kondo temperature associated with the coupling of this localized spin with the electrons in the leads. There's a delta, the correlation, superconducting correlation. And then there is an energy scale, the Zeeman energy, that we will try to use, that acts on the spin of the localized state, so inducing a Zeeman energy split in between these states. So these measurements of nonlinear conductance show that at zero energy, if you sit in this plateau, in this 0.7 regime, you have an overshoot of the conductance due to superconductivity. But if you increase the magnetic field, gradually you see that you go towards a single peak in the conductance, and then this peak splits. as one would expect from the splitting of a Kondo resonance due to the Zeeman effect. And this is a measurement done at high magnetic field that shows clearly this splitting of the Kondo resonance. So now, to conclude, I want to show you what happens in the 2 more minutes, 1 minute. What happens, and I cut down my presentation, but what happens in the superconducting regime? It's one important message I want to leave you. So in the superconducting regime, so now we have this localized spin coupled to superconductor, and let's see what happens when we apply magnetic field. So this is the phase diagram that you have already seen before at 0 magnetic field, and this is how we scan through the phase diagram as we move the gate voltage. So because there is a variable gamma, as I said in the beginning, it's very important. So the variable gamma. So in the superconducting regime, you see that we see a peak in the supercurrent. This is the measure of supercurrent, switching current, and retrapping current. There's a peak in correspondence of this shoulder in the normal regime, where that corresponds in the model to this peak over here. Now, when we increase magnetic field, so the domain associated with the doublet increases due to the Zeeman effect. And actually, our line starts to approach very much the phase boundary. And when this happens, we have a 0 pi transition. And so there, the supercurrent is strongly suppressed. And this is manifested by this suppression of the supercurrent. But if we keep increasing the supercurrent, so here it's totally suppressed. If we keep increasing the magnetic field, then our line cut goes through the doublet regime, and then we enter a pi regime where we get a recovery of the supercurrent due to the pi junction effect. So we have a non-monotonic dependence with a recovery of supercurrent due to pi effect. So you have magnetic field to conclude. So basically, the magnetic field is in the beginning is killing the supercurrent, but then eventually causes the reemergence of supercurrent due to a 0 pi transition. So this is the summary of my talk, and so I'm ready to answer some questions. Thank you.